all power series. What we're going over right now is the Maclaurin, and then in the next case we're going to look at the Taylor. But in general, it's all power series. All right, so to find the interval of convergence, good news is there's only one test. There isn't like 10 tests in this. The usual procedure for finding the interval of convergence of a power series applies the what? Ratio test for absolute convergence.
All right.
This is actually very good news because there's only, don't you love it when there's just one way to do something? And this is the case. Okay, so let's state what that is. What does the ratio test state? It is P equals, and it's for absolute convergence, so it's the limit. You take the k plus 1 term, a sub k plus 1, divide that by a sub k, take the absolute value, and then let k go out to infinity. Okay, so that's the actual ratio. Now tell me, by the ratio test, when does this converge? Yes. Right? That's the only test that we need to know. Okay, so that should be good news. Okay, so then in all these examples, you're trying to find two things. The first thing is, what is the interval of convergence? And then the second thing is, what is the radius of convergence? Okay, so we're going to be using this ratio test that we stated up here. So here's our series. So we know that this is a Maclaurin because, how do we know that? Because it just says x. So it's just like having an x minus 0, so it's centered at 0. So this is a Maclaurin series. So I'm going to write out my ratio test. So it's P is equal to the limit, and then it's going to be absolute value, a sub k plus 1, all over a sub k, as k goes out to infinity. I always write out the original one first, and now I'm going to start substituting it in. So then that'll give me the limit. So this will be x to the k plus 1 all over x to the k as k goes to infinity. Okay, then you're going to do the simplifying on this. So it's the limit, and then I'll write it as x to the k times x all over x to the k as k goes to infinity. And then we can cancel. Cancel, cancel. So then you end up with limit as k goes to infinity of the absolute value of x. So what we need to do at this point is to take k out to infinity. But since we don't have any k's, it's just going to be this. Right? So that's just going to equal absolute value of x. Right, so that is the basic ratio, and you're not going to get just a numerical answer usually. You'll get something with x's in it. So now I want to force this to converge. How do I force this to converge? Make it what? Yes, less than 1. Okay, so I make it less than 1, and then at this point I'm going to now write it as an actual interval without the absolute value. So it's going to be, x is going to be less than 1, or it will be greater than a negative 1. All right, so it lies in between those two things. Okay, so we've got a scenario that is going to be the third case right here. So it's kind of obedient, but there's some disobedience, right? So now we want to know, well, what about those endpoints? So now we want to determine, is it including negative 1 and 1, or is it only including one of them, or is it including both of them? Right, so that's what we need to test out. So now I'm going to do the part that's with endpoints. Okay, so with the endpoints, I take the one endpoint. So this would be like equivalent to a negative r. So I want to know, the first case is when x is equal to a negative 1, I'm plugging it back into my original series. Wherever I see an x, I'm going to put in a negative 1. Right, so that's going to be negative 1 to the k power. And you're taking, of course, k is equal to 0 out to infinity. So now this takes us back to our previous lessons, and you're going to use all those 10 convergence tests and determine what this is. It oscillates. That's right. So if I write out a few, I can say a sub 0 is equal to 1, a sub 1 is equal to negative 1, a sub 2 is equal to 1, a sub 3 is equal to negative 1, and so on. So I get a 1, -1, 1. Therefore, what's the conclusion? Diverges because it oscillates. Or you could just say, by the basically you're looking at the divergence test and it's not going necessarily to 0, but it's wavering between two values. So what diverging here means is that it will not include this -1. All right, so then the second endpoint is at x is equal to 1. All right, so if x is equal to 1, I'll be using k is equal to 0 out to infinity, and then it's going to be 1 to the k power. What is 1 to the k power? 1. So it's basically just 1. So it's what? 1, 1, 1, 1, 1. 1. Does it converge or diverge? So this one oscillated. This one diverges by the divergence test. Yep. So by the divergent test, the limit of 1 as k goes to infinity is equal to 1, which doesn't equal 0, therefore it diverges. Okay, so it diverges at both of the endpoints, so now we're ready to write out our final answer, and I'll do it up here. So I'm going to just use the abbreviation interval of convergence, that's going to equal -1 is less than x is less than 1, or you could write it as an interval notation as -1 to 1. So those are parentheses. Okay, so that's the first part. And then what is the radius of convergence? R is going to equal, so in terms of a diagram, this is what you're doing. You're at a Maclaurin series, so it's going to start at 0. So it can go to the right one, or it can go to the left one here. So it's kind of like a circle, where if the radius is starting from the center, and you can go 1 in any direction. So what is the radius on this? 1. Those are the two answers. So the interval of convergence is -1 to 1, not including the endpoints. And then for the radius, it's just going to be 1. So that means that for this particular series, no matter how much you try, you can't get it to fit to the right of 1 and to the left of a -1. And that's sort of the case that we just used. So this is a algebraic or the calculus way of showing what we had shown here. This is the best that it gets. So from here to here, that's the best it's ever going to get. Even if I go x to the 100th power, it will not get any better. And so that is what the interval of convergence is referring to. Okay. All right. How am I doing this time? Okay, pretty good. Okay, so then for the next one, we have x to the k power all over k factorial. So I'll start off with p equaling the limit, and then I'm going to write up the general, which is a sub k plus 1 all over a sub k as k goes to infinity. So then this time it'll be x to the k plus 1 all over k plus 1 factorial, and I'm just going to reciprocate it at this point. So this is k factorial up on top and x to the k in the denominator as k goes to infinity. And it's all absolute value, right? So we're not dealing with any negatives on this. So then that's going to equal, so rewrite it. Okay, now I know some of you are thinking, do we have to keep writing all of this out? It's best to write it out just so that you can show your work, and try not to do things in your head. You'll make a careless mistake, right? So then this will be the same thing as x to the k times x, and then you have your k factorial, and in the denominator it'll be a k plus 1, and then I have k factorial and an x to the k. All right, then you have the part where you have to cancel out. Cancel x to the k factorial, and this. Okay, so in the next step, I'm going to actually rewrite it so anything that is affected by the limit will stay, and anything that's not affected by the limit, I'm going to bring it out to the front. It'll just help you to solve it better. right? So I have this x up here, which is not affected by the x going, or k going to infinity. So I'm going to take this absolute value of k out to the front. It's kind of like a constant. Even though it's not a constant, it's just not getting affected. And then I'm going to rewrite whatever is left over. So you have the limit as k approaches infinity. And what is left over after I take it all out, or take the x out? 1 over k plus 1. Yep. So then that's going to be absolute value. Now I'm going to evaluate this part. Okay, just use your horizontal asymptote rule. What does this become? 0. So that's going to equal, I have my absolute value of x. This limit goes to 0. Anything times 0 is equal to 0. Right? And now I need to go back up here and write out, I want it to converge. So I have to say, is less than 1. When does that happen? All the time. Best case scenario. All right, so this is always true. Therefore, what we can say is the interval of convergence is going to be all real numbers, negative infinity to infinity. And the radius of convergence is equal to infinity. Right? So that means that as I keep adding more and more terms, it's going to get better and better. And this happens to be e to the x. So if you have an equation that's e to the x, as you keep adding more and more terms on the polynomial, it gets better and better and better. Right? And so what we're actually showing is, if you go to page 15, the thing that I just showed before was this. See how they say the interval of convergence is negative 1 to 1? And what I just showed you here is e to the x, negative infinity to infinity. So it's good for the entire real number line, and it'll match up for every single part of those. Okay. Okay, I think we can do this last example before lunch. All right, so we have k factorial times x to the k. So we have p, and that's going to equal the limit. It's going to be a sub k plus 1 all over a sub k as k goes to infinity equals the limit. So this will be k plus 1 factorial times x to the k plus 1 all over k factorial times x to the k as k goes to infinity. Absolute value. All right, simplify this. I'll do it down here. So we have equals limit. So k plus 1 factorial is k plus 1 times k factorial. And this is going to be x to the k times x. And the denominator, k factorial, and a x to the k. So you have as k goes to infinity. So this will cancel out, this will cancel out this and this. Okay, so just like the previous one, I'm going to pull out anything that is not affected by the k and then leave everything else in there. So I have an absolute value of k that I'll bring out, and then I'll write it as the limit absolute value of k plus 1 as k goes to infinity. Okay, now evaluate this. What is the limit of k plus 1 as k goes to infinity? Infinity. So you end up with absolute value of x times infinity, which equals infinity. Where does it converge? Right here, which is less than 1. And when does that occur? Never. So it's never true. So basically this is the worst case scenario. I mean, in terms of work, it's kind of a good case because you don't have to do any more work after this, but basically it's just saying that at the one single point of x is equal to 0, it obeys. On all other cases, it disobeys. All right, so then we would say interval of convergence would just be at the single point, x is equal to 0, and the radius of convergence is equal to what? Is 0. So if I were to look at this here, it'll just be this. That's it. One itty-bitty part right there. Very rebellious student or teenager. I don't know. What's one thing that he might obey? Maybe his bad friends or something. That could be it. Okay, we're going to move on though. All right, I thought that we would take longer on that. So, the next example. What time am I at? 15. Did I pause at all? So many.